Okay, sorry for the delay. So this is where we stopped last time. So we essentially, just a quick reminder where we were. So we were starting running in main, right? And we essentially successfully initialized the hardware, reached the main function. Everything is fine. We have a question.
Yes, I have a question. Is the quiz done already?
Quiz, I think, is due on.
Well, it's already, right? Because I have a question for the quiz I want to ask.
It's okay, ask. No, it will close on.
So I looked at the source code for K in and plot. Okay, and it goes forward.
Okay,
But your graphic on the previous slide goes backwards,
can be.
and that's different than what source code.
Good question. So you're saying that this diagram
Backwards.
No, actually, I think I was going forward here. So I first added this page, then this one, then this one, then this one, right?
Okay.
So I started from with v start, and I was going to whatever k init one end or something like this, right? We can review, but it seems to me that this figure is correct. Do you agree or disagree? I can't be wrong. That's totally fine. Like it's easy to get confused, right? Like which way it goes.
Well, yeah.
No, okay. I mean, I don't mind. First of all, the quiz is due tonight, right? But because I assigned it very late on Friday, so it's totally fine. And I don't mind discussing quizzes in the lecture because, I mean, the quiz is not there to filter whoever is smarter or anything, right? It's more like let's learn together. So ask.
The quiz asks, what is the first one list after it's been initialized? Something like that. How it's phrased, but
me neither. So, and I can change I might change the naming from or the phrasing from one year to another.
It's like the current end is at whatever. It's first page added to it.
Okay, honestly, I don't mind. Okay, sure. Let's answer this question, but let's spend 10 minutes on that. And let me just remind everyone what's going on, and then we will come back and specifically try to answer this question. And I do appreciate it because again, it's not about confusing you. Yeah, I do ask a semi-confusing question on purpose, so you spend some time thinking about it. Questions can be wrong, answers can be wrong. It's all fine. If you took your time and thought about it, you did your homework essentially, and so let's do with it in a second. But it's good actually. So this is kind of the discussion which I wanted. So, but what I wanted to remind you guys is that we're sitting in main, right? And I somehow lost my slide with main here, right? And so the very first thing our high level goal and the goal for today is to execute this function. And this function will construct the very first real page table which will have 4 levels and will map 4 kilobyte pages, right? So it will be PML4, PML3, PML1, and so on, right? In order to construct this page table, last time we said, okay, we need to have some ability to allocate leaves for this page table, because each node of this, okay, leaves is probably a wrong word, so just node. Each node of this page table will require a page of memory, right? In order to allocate these intermediate levels, we need some kind of a memory allocator. So a support for a function which returns a 4 kilobytes of memory page aligned, right? And for that, we said, okay, we're going to build this simple memory allocator, right? And the simple memory allocator is organized as a linked list, which is we were just discussing a second ago. And this linked list specifically is maintained as a pointer to the head of the list, and the elements of the list live within the pages themselves, right? So there is the data structure which we're using has only one element. It's next. It's pointing to the next element on the list. It's very simple. It's as simple as it gets, right? in fact, right? And the way we allocate memory, we just, whatever, if it's a list, it used to point here, we read the next, we read the head, update the head to point to the next, and this is the state of our list, right? If we allocate more, like gradually those pages are removed from the list, right? And if we're free, we add them back, right? And the question which we just had in like a second ago in class is that in the quiz, I asked something about this list. So let's go to the quiz real quick. And I will, for a second, stop sharing just because I'm not sure that I will not be, I don't want to leak the names on the quiz and results. So just let me, so like this, I have to unplug it, I'm sure. I'll go to the question. What is that grade called? Just to specifically, it's quiz number 6, right? Or yeah. Okay, cool. So yeah, last question. Jesus, I have answers right here. Okay, sure. Let me copy the. Let me copy this question. Okay, I can probably do it like this. Jesus, like trying to make sure that I'm not leaking the answers right away, and it's harder than you guys think, but I'm almost there. Although it's actually kind of not there, honestly, still. Just a sec. Copying. Click. Okay. This goes here. Just a sec. And I will paste it here. Okay, sure. So ready to go again. With this, back to sharing. We're sharing. Okay, this is the question I'm asking. So I'm asking, what is the virtual address of the very first page added to the kernel memory allocator, considering that the kernel memory allocator has been initialized? I assume that the kernel is linked such that the AND symbol is at the virtual address, whatever. This is the address.
So my question about this has just been initialized. Does that mean K init 1 is just started or K init 1 is complete? And it's like the first one added would be the end of the list, not the head of the list. Right?
Well, I agree. So I agree that there is some like ambiguity here. What I mean is the very first page added to the kernel memory allocator. That's probably
30K.
Yeah, that's what I'm asking, right? And it kind of clarifies everything, right? So, but just again, I get it. I apologize. The way I wrote this is odd, right? But what we really have to look at, right, and is okay. We actually have it on slide, so we don't have to go to the source code. So I just wanted to switch to the source code real quick, but not worth it. So what we have here is that I think this figure is correct, right? So the very first page which gets added, the list, and okay, how to verify it. So we go to this routine and we say, look, how do we initialize the list? This is how we compute K init 1 and. This is computed in such a way that fizzstop, like they try to figure out whether fizzstop is greater than 1 gigabyte, and if so, just pick 1 gigabyte. If not, just make sure that you're not trying to touch memory past the currently mapped region, because here the list itself will live within this right above the kernel. And if you suddenly touch a page outside of this first gigabyte page, then you kind of immediately triggering a page fault because you will try to update this element of this list, right, and get it right, will trigger a page fault. And what's going on here is that we say, look, sure, we take two arguments, and symbol error and k init one end. We go into this function, so it uses the names, local names, or virtual start, virtual end. We use this function free range, which goes from virtual start to virtual end. If we look inside the free range, what happens? We start running a loop. What we're doing here, we take virtual start, round it up to the next page, get the pointer p, and then the p goes in the increments of page size and does the k free. So the very first page which gets on that list is essentially, tell me. Okay, do tell for everyone at this point. Question.
Well, so I was just gonna clarify like what that means on the image you have of the like news list.
Yep.
So and the one next to N is the first one that was added.
Yeah.
Okay. So,
This one was added first. Then we were like, because this is how the loop goes. Oh, sorry, where is it? You say I'm looping here from starting from P, incrementing P by P plus page size until I reach until its P plus page size is less than VN. So we don't want to spill into the.
and then there's
Yeah.
and symbol.
That's where the and symbol
So
points.
that's
Yeah. Well, rounded up to the next page. Right. So if you carefully, like maybe it's a little ambiguous here, but n might fall somewhere here, right? And then we round it up, and then all the pages starting from the next page and on will be free pages. Make sense? Any other questions about it? Yes, no? Okay. Okay, anyone else in the class? Any questions about the free list? All good? Okay, it will come back more or less like there will be questions like that. Okay, cool. So we have the memory allocator. We know how it works. And now we're essentially ready to say, look, let's execute the second function in main. And this one, the goal is to construct our new page table. Because right now, what we have exactly this diagram. So we have a boot time page table, which has a root entry PML4. It has two leaves, identity map and kernel map. Those leaves map these two regions, 1 GB regions of virtual memory. One is mapped from 0 to physical 0. Another one is mapped from kernel base, which is right now chosen to be at 8 TB to the same 0. So this line, right? Make sense? And we say, look, we needed this page table to boot, but after that, we really want to have flexibility to construct any page tables we like, right? Okay, so if I ask you a question, so what do you think has to happen inside this function? Like we already talked about it. The goal is to construct the page table, 4-level page table. What do we want to do? And again, at a high level, let me reemphasize the goal that we kind of said that we don't want this region because we want user memory to live here, right? We only want to map this to physical 0, right? Because we remember I talked about it. Let me just come back to this for a second. So at a high level, for each process in a system, we want this layout of virtual memory. This starts at 8 TB. This is not really accurate because we don't really map all memory up until 16. We map everything up until FISTOP. It will become clear today as well, right? But the lowest addresses of virtual memory are all user addresses, and the addresses above 8 TB are kernel. And the way we mapped it was a shift similar to how we did it with the first page table So the question is like, what should be inside this function?
Does it have to map like, and then 0 to physical 0, and then add just 8 terabytes?
Not exactly. Okay. And I wanted to like we say right now we don't even have a process yet, right? So we really want to map just the physical memory from 0, and ideally we should map to all available physical memory. Let's assume this machine has 512 megabytes of physical memory. Since x86 doesn't dynamically detect the available physical memory, and the reason is that it gets a little complicated. You have to talk to BIOS and query, and the protocol is a little bit like complicated and varies from hardware to hardware. They just say, look, we will declare a constant, which is called a physical top, phys-top, and it's roughly 234 megabytes. And everything above, even if you have physical memory, x86 just simply ignores it. And what happens here, we say, look, we're going to map this with the shift, with the 8 terabyte shift, because we say, look, we're going to leave space for user memory, which we will map later when we'll start creating user processes. But right now, map everything above, like starting from the kernel base constant, which is 8 terabytes, and map like 4 kilobyte pages one by one. Since now we have granularity of 4 kilobytes, we don't have to like just ignore and map everything with the same permissions. And we say, look, we will be clever about it. And this is how a real kernel does it as well, just because the reasons are security, but also to catch possible bugs early. If you say, look, the first megabyte of physical memory, we might have to write it into it. So this we will map as read-write. Then there will be a kernel text section and a read-only data section. Okay, sure, let's map it as read-only. Then will be kernel read-write data section. And we control this layout because we're using a linker script, which I mentioned the other day. And we essentially can say, okay, this is how we want the kernel to be compiled. So it's not random. We actually control it. And this region we will map with read-write. This we will not map because, okay, sure, we're not using it. We're only using memory up until phys-top. So it like this one becomes mapped as read-write. And there is also like at some point, this hardware manufacturers, they ran out of this BIOS space here. They say, okay, sure, let's reserve a little bit of BIOS space at the very top of the 4 gigabyte. And this like chunk, which is like a tiny piece of like, essentially, if you write into this physical memory, it just goes and reaches over the PCI bus, reaches a physical device. We will map at the very top of the address space. Like just, no, we could have chosen like different layout, but that's kind of meaningful, right? So essentially, but all this memory is mapped with a 8 terabyte shift, right? So you don't have to map twice. You don't map anything here for now. This is reserved, right? So, make sense? Clarifies a little?
We got rid of the PLL for entry 0 again.
What do you mean?
Yeah. Or is it still mapped as the identity map?
It's identity map still, because this right now our CR3 still points to this HTML4, and we didn't change anything. Like everything what we did, what you saw on the screen. So I didn't skip much. I mean, I skipped like maybe 5 lines of code or something. Right. So we didn't discard it yet. So it's still mapped. This region is mapped, but in our future, yeah, we're not going to use it in the next page table, because the hope is that right now we'll create the page table, which will throw this away. We'll only have this region mapped with the 8 terabyte shift. And when we will start creating processes, for each process, we will first map this region. And then as we start loading the process text, we will map something here, right?
And then each page in the K init one, do we need to make a page table entry for each of them? Or
we'll see in a second. I mean, I get it. It's a little confusing, but give me first an outline of a function which will try, if you look at this map, let me clear everything from this slide. the end goal is that obviously one page from here will be mapped to this one, right? The next page will be mapped here and so on. How the function which builds the page table should look like? With the code or with? Yeah. Let me show you. This one, yeah.
Yeah, I guess.
Yeah.
And then you get rid of.
No, hold on. Do we remember why our page table maps this to virtual? Okay, for everyone, and maybe, I mean, it's worse figuring out right now than later, because if you don't understand this fully right now, then your life will become more and more miserable. Let me go over this diagram again. So we have physical memory, right? So it starts at 0, goes to some number. We only handle it up until physical top, right? Remember, we started booting at the low addresses, right? Essentially, our instruction pointer when we started booting was first at 7C00 somewhere here. Then we mapped, when we jump into the entry point of the kernel, we started executing some assembly code, right? And when we switched to protected mode of execution, or we said that we enabled paging, right? We said, okay, we cannot do it atomically, because the instruction pointer will still show up here. It will be RIP, but points in the low, like around 1 megabyte, right? And then we said, okay, but then in the end, our end goal is to end up with the address space. I will show you this slide, in which the kernel is mapped at 8 terabytes, right? So our instruction pointer will be pointing somewhere here. So this is where the main function is linked, right? So main function is linked at something like 8 terabyte plus 1 megabyte plus some short delta, right? Agree with this? So this is the reason why we needed 2 entries in our first boot time page table, because if we don't have, and this is what I'm asking on a quiz actually, right? So I'm asking what happens if this entry is not present? Okay, which line was which page fault? What happens if this entry is not present? Which line will page fault, right? So how many people answer this question and understand the answer? Like roughly 10. How many people attempted to answer but still don't? Okay, so then follow like I let's do it again. Do we understand and again, it's worth spending time, because again, this construction, and it's kind of representative for all modern kernels. Something like that always will be there. So understanding it once makes sense. Remember how everything started. So BIOS loaded us at 7C00. Our instruction pointer was specifically pointing at 7C00, right? And then like we ran the bootloader went to disk. It was still like running somewhere at 7C00, loaded the kernel, ELF of the kernel in memory, in physical memory, at the address, which is 1 megabyte, right? It's just because we knew that everything below 1 megabyte might be occupied by other, like by BIOS. Okay, sure, at this point, we're done with the bootloader, and the bootloader jumped into the entry of the kernel. And we're still running, I think we're running in 32-bit mode, but there is still no paging, right? So we have segmentation, 32-bit segmentation, so we can we're sitting here, but this layer is not yet active, right? And the moment we advance through this entry code of the kernel, we say, sure, at some point, we want to enable paging. And in order to enable paging, and let me probably at this point, I have to switch the slide deck. Do I? Or, okay, let me. Okay, like don't wanna I didn't want to switch the slide deck, but sure. Okay. So this is our boot lecture. Okay. Let's see if we can actually erase from previous. No, doesn't work this way. Just Control Z maybe. Now I have to manually erase all the drawings, which is not fun, but we can do it. So it's essentially a recap of the boot lecture. And what we're doing here is something like, this is the entry point of the kernel. We landed over here. Our goal is to enable paging. Our instruction pointer, like when it executes this line, has the value of something like 1 megabyte plus some short delta, like very small one, like because the kernel, roughly speaking, we told the linker to link the kernel at 1 megabyte, but of course, like we don't control the compiler. There are some instructions which might be placed in front of this instruction. So roughly, this is the explanation for this delta, right? But essentially on this diagram, like segmentation is enabled. So start symbol is here, your instruction pointer points right here, right? Paging is not yet enabled. The moment you try to enable paging, meaning that you say, like specifically, you will reach, let me show you which instruction enables paging. Like for example, this instruction says, okay, sure, paging is on because we said we read control register 0 into EAX, set a specific flag which says paging enable, write it back. The very next instruction after this says paging is on, right? But the instruction pointer will still be somewhere over here, right? Because we executed the move instruction, and our instruction pointer was pointing here. So obviously the instruction pointer gets incremented and points to the next instruction, right? In our instruction stream. And this next instruction happens to be load GDT, right? But instruction pointer is still pointing at something like 1 megabyte plus short small delta, right? Make sense? So if you suddenly at this point, now this is on, right? Because we said paging is on, so the whole like translation level falls through. If you suddenly don't have this entry mapped, what happens? Like people who know the answer. A page hold, right? Because roughly speaking, or specifically, this entry is not present, right? So the hardware says, okay, sure, my CR3 points here. You said that you want paging. I try to walk this page table. This entry is not present. It's page fault immediately here, right? Make sense? So page fault will be triggered by which instruction? Which one? With this one? Yeah, sure. I agree with this. By the way, if you, for the quiz, you should put the number something along the lines 1170, but these numbers might be from an old kernel, or maybe it's from a new, I'm not sure. So just double check that like the link online. More specifically, what I want is I want a number from an official printout, which is where, like, let me quickly figure it out, not this one. Okay. Like print out of its source code. So specifically here. So you go, you say entry. It will take me some time to find it. Start 64-bit. So yeah, it's actually the right number, 1170. So this line will trigger a page fault. Does everyone agree? This is the answer to the quiz. Any questions, Rick? So hold on. what you're saying, if I understand correctly what you're asking, and correct me if I'm wrong, what you're saying is that imagine this line actually does trigger a page fault, right? You go through the interrupt processing pass, and the question you're asking, can you still recover from this? Is that what you're asking? Mm-hmm. Okay, so we haven't yet discussed the interrupt and a page fault processing pass. So a page fault is a special flavor of an interrupt, which is called an exception, which is defined by Intel. However, the moment you set this paging enable flag, even in order to fetch the interrupt handler or exception handler address, you will have to go through the virtual addresses. It theoretically possible that you're so clever that you configure your interrupt descriptor table in such a manner that those interrupt entries point to the higher addresses, and maybe there is a way to recover, but that's like, it's a little tricky to set up. And I'm not entirely sure that it's possible. Potentially it's possible, but just like the hardware is very kind of like, it's obedient. You said, okay, I want paging, it will force you through the paging. Interrupt handlers also run in a virtual, like in a paging mode. So everything, the stack pointer, instruction pointer, everything will be forced through the paging mechanism. There might be a way to kind of like figure it out and save it, but I'm not sure. Another question.
Lower your one.
So again, this line is what?
That will take off. We did not have the lower.
Correct, right? Because your instruction pointer, if you don't have this entry, your instruction pointer is still here. Segmentation is set up. You base is 0. You don't add anything. You just essentially fall through. But this mapping is not set up, so it's like empty. And because just you say like there is no present bit here, right? Or something, or it's just all zeros or something, right? And at this point, you page fault. Make sense?
Yeah.
You can play those games, but maybe I did not emphasize this enough. On x86 64-bit machines, you cannot change this base. It's always fixed to 0. That's Intel just said, okay, we're going to simplify segmentation. No one was using it for a while. We just say it's always 0. But yes, you're right in your thinking that there might be like some esoteric construction which allows you to somehow still handle this situation. But again, I'm explaining the simplest, probably the simplest route. And the simplest route is to have these two mappings. Okay, sure. Then I will ask you a question. What happens if the other entry is not present? It's again part of the quiz. That's why. What if this entry is not present? Sorry, just made a mistake. What will page fault? Which line?
The jump to main.
They jump to main of the kernel. Correct. So because you say, look, I'm so clever, I set it up. Sorry, like this guy stopped working for a second. I executed this instruction correctly. I executed next instruction correctly. I keep going, like I set up, like this is my 64-bit global descriptor table. You long jump to start 64-bit, which you start executing this instruction. This is still 1 megabyte plus some delta. At this point, this instruction is still 1 megabyte plus some delta. But here you're loading the symbol main into the register RIX. And this symbol main is compiled to be at 8 terabyte plus 1 megabyte plus some delta, right? And this instruction, which jumps, this instruction actually will succeed, I believe. Or not? Probably not. That's a good question.
That's the dereference stats.
Yeah, I agree with you. I agree with you. Yeah. So most likely this instruction which has to. This is a great question, honestly. and I don't know the answer. Maybe the hardware works in such a manner that it actually allows this instruction to succeed. You tried? No, like, disagree. But okay, so we probably should take both answers, like this line 1182 and whatever, the main itself should be taken as the right answer. I probably, in my quiz, I configured that this line page faults. Now, after looking at it very, very carefully, I might, because this is just, roughly speaking, this sets instruction pointer to 8 terabyte, but it's not yet executing the next instruction. So maybe this one actually succeeds in the next one. And it's a good question, like just, I mean, how to try it? You can try under QEMU, but QEMU may not faithfully emulate hardware. So you really have to try on the hardware. Most likely, yeah. But I think I'm taking this as the right answer. Like, if I remember how I configured the quiz. And I don't really know the answer myself. So it's like, it's in the wood. But okay, but no matter whether this instruction page faults or the next one, do we understand why this page faults, right? Is this clear? Yeah, okay, that's why we need this second entry, right? So we need this one to be present, then like essentially we say jump to RAX or something, right? RAX points to somewhere here, and the very next instruction after this jump, sorry, like essentially RAP, let me just maybe disconnect this thing or really close this. And restart, and hopefully my Wacom will work. Like essentially after you did the jump, this is a jump to RAX. This RAX contained main, and main is a symbol which points to here. And at this point, you switch to higher addresses, right? And after that, you will never go back until you start executing user code. The kernel will always live in this address range, right? Make sense? All good. So we understood how we ended up here. Now, back to my wonderful question. How to construct the page table. So we're here. So our goal is to map everything with an 8 terabyte shift. Like essentially virtual page, which sits exactly here, will be mapped to virtual, like physical page number 0 will be mapped to this virtual page number, which corresponds to this 8 terabyte address. How do we construct a function which creates a page table, which does these mappings? Everything here with an 8 terabyte shift. The reason for you to wake up is because this is your homework number 3. Essentially, we'll ask you to create a page table in a very similar manner. So it's not hard. Okay, but can anyone try to guess what's going on inside this function, which builds the page table? Okay, let's take a slide, like a rough overview. At a high level, what we need to do, we say, look, we want to construct a page table. We say, look, we will have 2 inputs, a virtual address, which we want to map, and a physical address where we want this virtual address to be mapped. We take this virtual address and split it into this like 4 9-bit components, right? Because those will be the indices. And we want a page table which maps this address correctly, right? What we need to do is we say, look, if we don't have, it's a brand new page table, so we don't even have PML4 level. So we'll have to allocate it from the allocator, right? Sure, we just simply go and allocate it, right? So we get this page. After that, we say, look, Jesus. After that, Say again. Right, you split them so you can reason about which you can reason about this. You can reason about this 9 bits will choose one entry in this PML4 page table, right? So this yellow, highlighted yellow entry. But you have to allocate all like PML4 level. And you say, look, sure, like if I just allocated it, my next goal is to connect PML4 to PML3. So essentially you say, look, there might be a chance that this entry was like PML, this node of PML3 was never allocated before. It's a brand new page table, right? So there might be 2 cases. Either you will have to allocate it or not. If you have to allocate it, you allocate it and you just connect them with this pointer. You say, look, like it's a page table. So my root of the page table, PML4, connects to PML3 level in this manner. Make sense? And you just like say, okay, that's my code will be doing this. And then you say, sure, what about, what are we doing next? And the next thing is that like we say, sure, then we take these 9 bits and they will point us to the entry inside this PML3 page table. And again, there might be 2 cases. Maybe this entry, the next level is already allocated or not. And if it's not allocated yet, we just again go to the allocator, allocate PML2, connect them, do the same from PML2, you check, like use the next 9 bits, you say, is this entry already allocated? It might be, might not. If it's not allocated, you allocate this PML1 node. Finally, you say, look, I'm using PML1 index to locate the entry in this PML1 node. And in the end, you say, look, I found this entry. You say, I'm mapping this virtual address and the pass through the page table, this pass is encoded by this 9, 9, 9, and 9 bits. But the physical address which you're mapping, you just have to write here, right? And essentially, this is what I have this here on this diagram. I say, we're going to put in this entry a physical address itself, plus the mapping flags, like read write, read only, present, and so on, right? Makes sense? And after you've done it, you say, look, I did 1 bit of this mapping. I mapped 1 page to 1 physical page. You say, but I want to map the entire region, right? So you actually iterate and you say, look, now my virtual address is virtual address plus 4K, physical address is plus 4K. And you kind of like, at this point, like all these intermediate nodes will be already allocated because you just walk through them and you can just navigate to the next entry in the leaf node.
Okay, so are we going from like 0 to the end symbol? So like the end rounded up or whatever?
Almost. We are going from the 0 to the fist stop. End is somewhere here because this is where the kernel data ends. And then the kernel says, I will still handle some amount of physical memory above end. And that will be my free available memory. But I'm only going to be handling supporting up until fist stop because I'm so lazy that I'm not going to query at runtime how much physical memory is available. In a real kernel, you do query.
So are we telling the page table which pages from our K-init1 are free or unfree?
Exactly. So how are we using this memory allocator, which we just discussed? So how is it used in this code? There's a hint here.
Well, we get some pages that are inside the kernel's memory space, but
Okay, what's like it worth actually zooming in and understanding what's going on this slide. So what's happening is that imagine like it's a beginning of this function. You don't even have this PML4 level. You have to go to the memory allocator and ask the allocator, give me a free page, which will store the page table. And this page is on the list, right? So specifically, it will be somewhere over here, right? That's the virtual address. In physical memory, it will be somewhere over here. And this is the very first page on this list because like head of the list points to this page, right? And this page will be at the very end of this K-init 1 whatever, and or something at the moment, right? Make sense? So this is the very first page which we're allocating from the allocator, right? And this is exactly this page. So I'm using it for storing PML4. As I move through my code, I say, look, but I need PML3 level as well. I go to the memory allocator, and the memory allocator says, okay, my head currently points to the next page. Like the very first page, you already gave it. So it's because it became our PML4. The next page on the list will be our PML3, right? Make sense? Agree? Any other questions about this?
So all of the PML trees, PML4 tree, store multiple addresses, but it's just the last one that's first.
Good question. Okay, let's ask the class. So what your classmate is asking, this pointer, which address is that? Virtual or physical? What are the options?
Physical, because virtual would have to find itself.
Correct. So it's actually physical address. And as a reminder, let me just quickly, I mean, it's kind of a bad reminder, but like whichever reminder I have, this is how the page table works. And there's 40 bits. Remember, we store 40 bits of physical address, which essentially a physical page number, because we know that this next page is page aligned. So the lowest bits are always zeros. So we, instead of storing the zeros, we put some flags here, right? But those are physical addresses. CR3 will hold a physical address, and all the entries in the page table, pointers to the next level, those ones, will also be physical addresses. And you're making the right observation. You're saying, okay, you're probably fooling us because you're telling us that this allocator returns a virtual address, right? Because we say when we do kalloc, it really, we just seen it, that the list itself, this one, this pointer is a virtual address. And you're saying, you're making a right observation. You're saying, okay, no, we cannot put the virtual address in a page table. That will cross the hardware right away, right? What's the trick? What are we doing here? When we are correct, so we actually putting a physical address and we're using the V2P macro. And how do we convert this virtual address into physical? Can you guess? It's very easy.
Just by subtracting that 8 terabytes.
Correct, because right now what we have, and it's not just not right now, throughout our kernel, all the physical memory will be mapped with an 8 terabyte shift into the virtual address space. So if you have a virtual address, if you say I will subtract 8 terabytes, you will specifically land on this physical page. So your V2P macro is just subtracting at 8 terabytes, just shifting the address. Make sense? And that's, again, that's by construction. If you break this construction, you will run into troubles and you will somehow, like every time you need to learn the virtual address of a specific page, you will have to somehow figure it out. We, on purpose, made it easy. We say, look, everything is mapped with 8 terabyte shift in a kernel. So it's very easy. V2P works, right? It's not always true, like, well, you will see in this, but in this kernel, it is true. Okay, question.
So we're running KALOC.
Correct. Any other questions? But the code is like essentially relatively straightforward. You say, look, I will allocate all the levels. I appreciate the fact that you observed that those are physical addresses. And right now we have a virtual address to the PML4, but when we're going to be loading it into the CR3, we will do V2P macro of this address to make sure that we load a physical address into the hardware register, right? Make sense? Okay, overview makes sense. We understand how it works at a high level. We're just working like with the 4 kilobyte increment, starting from like 8 terabyte plus 1 megabyte. And essentially here physical goes from 0 to stop. We go one by one, mapping pages, allocating these intermediate levels as needed. Intuitively, it feels that we will only allocate these 3 levels once, and only since we are mapping, I mean, like if FISTOP is 230 something megabytes, then we only need like a couple of, like some number of leaves here, but not a huge number, right? So only these PML1 levels will be allocated. Let's take a look at the code, how it's actually done. The reason we are doing it, I mean, I appreciate the fact that you do understand the outline. The reason we are going through this code, source code, is just for 2 reasons. First, this code will be coming back multiple times later in this class. Like a lot of this logic of the kernel will be managing virtual memory, essentially constructing address spaces. The reason is because, you know, the process is an address space, right? And a second reason is that you obviously, I will ask you to do the same in the homework. Okay, sure. So we have this function. It stands for allocating kernel page table or kernel virtual memory alloc, right? So, okay, let's look inside. So not surprisingly, there is something what says, okay, this setup KVM says, okay, I will set up the page table, which we just discussed, and I will return you a pointer to this page table, and we will remember it in a global variable, KPML4. And like later on, we're gonna switch to that page table by reloading the TR3 register. But let's first take a look at what's inside this setup KVM function. So the setup KVM is exactly as we just discussed. We said, okay, well, it's a brand new page table, so we're gonna allocate the root of it. So we call kalloc and get a pointer to PML4. It's a virtual address. Kalloc can fail, then we return 0, right? We might run out of memory because we will be setting up this page table for each new process. So this function will be reused later in the class. Okay, so what? Whole time. Wake up. So what is the address of this page? And everyone in the class, especially in the back row, is like this, right? Jesus Christ. Don't ask us. But like, yeah. Let's answer this question. I mean, I hope my poll actually encoded correctly. Okay, I activated it. Oh no, Jesus! Let me wait. Deactivate. I apologize. Give me a sec. Okay, let's do it again. Let me clear the answers. I assume you can change the responses, right? Let me just I activated it again. Just be more careful because it's on purpose a little convoluted. Allow changes. Okay, sure. Remember, we discussed it at the very beginning of this class. Like it's essentially organization of this free list. So and
So is there a function for the purple trees?
Yeah, like every time you will be deallocating this page table, you will free those leaves and put them back. We'll see it later. Every time we will be, for example, doing exact remember reloads, and the old address space was new one. The moment we said, okay, sure, we will succeed, there is no failure, we will deallocate the old page table.
So that's like a signal.
Yeah.
So it just adds.
Yeah, always at the top. Yeah. And I mean, like, obviously later on, it will be very hard to reason about what is the address, but right now we know the state of the system. The reason I'm asking this question is just to reiterate that again, it's almost like everything is known to us. You're looking at this kernel and you know how you set it up. So, like, question? Virtual. HTML4 is a virtual address. Let me actually for a second show you the answers. Okay, I'm not going to show you the answer. So what are the options here? So we roughly split, we actually split, okay, let me show you how we split. So again, the goal here is not to like penalize anyone or anything like that. Let me just quit the slide deck, show you the poll. So we're at this. So who can argue for the distribution is what is called bimodal. We have two potential answers. Some people argue about the address of the end rounded up to the next page. Some argue for k init 1 underscore end minus 4 kilobytes or something along those lines.
Yeah, I think it's k init 1. Because the k init 1 function goes till the end of whatever memory space it has. And so minus 4k would be the address of the last page. But that's actually where the head pointer points to because it was added last. Because it can only add to the head of.
Yeah, I agree with you. So does anyone? So, I mean, this is a very good explanation, and this is what I want to hear on the exam. So, like, no goofing here, guys, no guessing or anything, right? So people who were confused about it and say that address of end rounded to the next page, who can you support your answer? Because this is. Yeah. Only that worked like that in politics, you know. I revoke my vote. Okay, sure, but you got the point. This is the page which was added first to the list, right? So if we're looking at this allocator, let me start the presentation here. How much time I have? Who broke the clock? It's like it's yeah. So this page gets added at the very it's the very first page which gets added to this list, right? So list grows this way, right? So the very last page on the added to the list will be allocated the first one, right? And this last page, it's actually not like current based, like it's in practice, the last page is actually not the one which I was like, it's not 1 gigabyte, it's not 8 terabytes plus 1 gigabyte, it's just k init end, and k init end is well, you can argue with me, but I mean, like, yeah, that's why k init end can be two different things, either the fist stop or the 1 gigabyte, but it's always this like known as k init end minus 4 kilobytes, right? Makes sense? All good? Answered? Yeah, it's the last one which we add to the list. Obviously, since this is how we organize the list, it will be the first page which we'll get. Go back to what? You mean the on a poll? Okay, sure. Yeah, I'll push you 64-bit, or maybe I actually pushed some of. I'm pretty sure most of those. Yeah. 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 Okay, got it.
No, I going back to that question itself.
Oh, on the slide. Okay, got it. Yeah, this one.
The 32-bit one.
Yeah. Okay, you good? Okay, so I'll freeze the poll. Everyone is clear on this? And I mean, you say, okay, why is that I'm asking this nonsensical stuff, this low-level business? It turns out most of the time you don't need this knowledge. Once in a while, you start crashing, you start bugging, like your kernel bugs, you try to implement threading, for example, or some funky extension to your kernel. And you just suddenly at this point, you have to reason about what's like, which page is which and why it might crash. So this knowledge is useful, but mostly I'm asking is just this to just make sure that we all understand this basic setup. So roughly speaking, I just want to understand that, okay, sure, we just want to, like, everyone is on board with how virtual memory is mapped to physical, which entries are present, which are not present, and what we're building, right? Okay, cool. Back to the source code. We still have like 15 minutes or like 12 minutes. So essentially, like, okay, so this is the very first page which we allocated in the system. It's a virtual address. It's the very last page which was added to the linked list, right? So it's this k init one and minus 4 kilobyte or roughly in that neighborhood. And we got the root of our page table, right? We make sure that everything is set to 0 because who knows, maybe like why, maybe bias, maybe graph, maybe whoever was running before us put some numbers in that page, so it makes sense to, or maybe we're like later in the system run and we actually use this page for something different, right? So essentially what we've done here is that we allocate this page. Okay, sure. And now we say, for sure, what we're going to be doing, we will be using an array, which is called a kernel map. And this array essentially represents those different regions. And we just, for each entry on this array, we will be using a function which maps this region. And this function is called map pages. And this map pages will be coming back to this function many times. But essentially what it takes here, it takes the pointer to the page table, which we're currently using for mapping, start of the virtual addresses at which we're trying to map. And this K is a data structure, which is part of this array, the size of the region, and the beginning of the physical address, right? And permissions with which we map. So essentially what it allows us to do is just to have 4 entries on a kernel map. So like entry number 1, we're going to map it with read-only permissions. Entry number 2, we're going to map it as, oh, sorry, this one actually will be read-write. Number 2, like read-only part of the kernel will be read-only. Entry number 3 will be this one, read-write. And entry number 4 will be this bias region, also read-write. And to be more specific, this is the definition of this data structure. You say, look, it's a struct, has a virtual address, has a physical start and physical end. They also encode the size, and we have permissions here. And there are 4 entries in this definition. The first entry is an IO space. It's this one. So we say writable. It starts at its physical address 0, and we're going to map it at the kernel base. And kernel base is 8 terabytes, right? And it goes up to extended memory, so which is somewhere here, which like a little odd definition. Then the second region is read-only. We say we use the virtual address, or sorry, physical address of a data symbol. This is exactly where the data section starts, and data goes here. So it's essentially read-write region of the kernel and so on. Like you more carefully, you can figure it out. And this is the bias region, right? This is writable, this is writable, this one is read-only. Makes sense? Only 4. And so essentially we have a function which can map a region of continuous virtual memory to like continuous set of physical addresses with specific permissions. And we just call this function 4 times, right? Make sense? At this point, we say, look, well, what's inside this map pages function, right? This is the one which we, just to make sure that we understand, this is the one which is called here. This is actually the call stack. So we called from main, kvalex, set up kvm. So we're here, map pages. Map pages itself says, okay, sure, not surprisingly. And it would be nice to kind of like, to understand what's going on here, but you say, look, I'm taking virtual address as an input. I will, since I want to map this address, and you can set this up differently, but you round down to the previous page, you get address A. You do the same for the last address, virtual address plus size. You pass the size as an argument. And what you're doing here, okay, let me ask you the question. What is this code doing? Again, it does the mapping. We looked at the overview. Just try to explain. Can someone read me?
Well, if the page table entry is missing, it errors out.
Where, which line? Yeah, there is some panic here. Panic means that we don't know what to do next. That's unrecoverable error. Not the best way to write your code, but it's essentially like halts the machine and you go home. If you're on a plane, it just goes down. Another idea?
Yeah.
Yeah. Okay, let me explain. So it's a couple of minutes here. So what we're doing here is remember the outline. We say at a high level, what we want to do is that we want to, for each virtual address, we want to figure out an entry in a PML1 level of the page table and write the physical address plus flags into this entry, right? And in order to figure out the address of this entry, we have to walk the page table. So we have to like take these 9 bits, check if the next level exists. If it doesn't exist, allocate it. Go to the next level, doesn't exist, allocate it. So essentially, we have to create a pass through the page table. If it doesn't exist, we allocate as we go, right? And essentially, this is what's going on here as well. We're using this helper function, which is walk page table, right here, which says, okay, I will actually do whatever we have to do. I will return you the entry. And this is the key line here. This entry assigns physical address plus permissions plus the present bit to this entry, right? So you understand this line? This star here means that it dereferences the pointer and writes into the memory location under the pointer, right? Agree? And this walk PML4 essentially walks the page table and if needed, allocates those additional levels and connects them in a correct way. And this PTE is an entry, it's a pointer to this PTE in the last entry, PML1 level of the page table, and you're just writing a physical address plus the permissions, plus the present bit, right? Agree? Code suddenly makes sense. You say, look, if you get me this entry and I will, then everything like here, if you suddenly say that this is not present, then I'm panicking because this thing failed to allocate me the page table entry. Here, we just do this one single write. And if A equals to the right, to the last break, if not, you just increment physical and virtual addresses by 4 kilobytes, right? And you go it over and over again. So it's very simple piece of code, right? Agree? Okay, sure. So let's quickly take a look into what's going on inside I'm just like inside, like I have a couple of supporting slides, so I already explained it. Let's take a look at what's going on inside this walk PML4 page table. We're using again a helper function here, walk page level. And we say, look, we take a virtual address, we take a flag, whether we want to allocate intermediate levels or immediately return an error, and we're taking the level. And we start, in this case, we start from level 4, but this function can actually walk from level 2, level 3, and level 1 as well. Okay, so what's inside this function? It's relatively easy as well. So you say, look, sure, depending on which level you're asking me to resolve, it will return you the pointer to the next level. So if it's 4, it says, okay, sure, from this page there, I will use the shift. Essentially, what happens here is that you have a virtual address and you split it into 9, 9, 9, and 9 bits. And this macro selects these 9s. This macro will select the next 9. This macro selects this 9, and this macro selects this 9, right? So essentially, it just returns, like it treats this as an array, chooses an entry in the array, and essentially returns a pointer to this entry in the array. Make sense? However, it doesn't immediately return. Then it does this logic of, okay, what happens if this entry is not present, all right? And essentially, here we do all this additional logic. We say, if there is a present bit, we just figure it out and go to the next level. If the present bit is not set, we allocate the next level, assign it to this pointer, next page there, set the next level to 0, right? Because we just allocated it, and we connect the levels, right? And if you say, look, I started from level, for example, 4, at the very end of this function, you recurse into the next level. So essentially, you reuse the same function over and over. So starting from level 4, you go to level 3, you go to level 2, you go to level 1. Essentially connecting all these intermediate levels as needed, right? Okay, so essentially, like, we probably have to quickly come back to this next time, just because I ran out of time, sorry, but and memory as well. But we are very, very close. So essentially, if you have the logic of how it works, so we'll come back to it and we'll be done in a second. Question?
I'll have to say that.
Yeah. Yeah. So, but today I'm gonna push you 64-bit